Hey everyone, I thought today I'll show you how to create a custom IK solver using control rig. At the end of the video, I'll tell you why I think it's a good idea to be able to do that. But for now, let's just get straight to the graph. So in that scene, all I have is the three controls that I need to create that rig that I've already set in the setup event. So the IK and the root control, this guy, are just matched on the bones in that position, and the up vector is matched to the second bone, except with an offset of 30 units in the back. So the first thing we're going to do is we're going to create a transform that is going from the root and pointing to the IK. So I'm going to use an aim math node, and our input transform is going to be the roots, because that's where we're starting. Our target is going to be the IK position, so I'm plugging that here, and our secondary target is going to be our up vector position. So just like that. In my case, the axis of the secondary target is -1 in y, so I'm updating that. So let's see what this transform is looking like. Make sure we've got everything correct. Let me make that a little bit bigger. And let's see. Yeah, we have a transform pointing at the IK, and the up vector is also here for the secondary axis. Okay, all good so far. So now it's time to do a little bit of math. If you remember your trigonometry class, this is a triangle from the first joint, the second joint, and the root to the IK. And so we can use the law of cosine to define what should be the angle, the angle of the first joint. So if you Google law of cosine, and we look at this little triangle, if this is the root and this is the IK, we have A, which is the length of my first joint, C is the length of my second joint, and B is the length between the root and the IK. And if we have these three values, we can calculate the angle gamma, that is the angle of my first joint. So let's do that. Fortunately, we don't have to remember this or even recreate that equation, even though it would be possible in control rig. We can use directly the node law of cosine that is available. So same values that we've seen on the little drawing. So A is going to be the length of my first bone. To make it easier for me, I created this variable, which is length of A. And I set it to what I know is the length of my first bone. So I'm just going to plug that here. B, as we said, should be the distance between the root and the IK. So let's do that. We're going to grab the position of the root and look for the distance to the position of the IK. And that's going to be B. And C is the length of my second joint. So same thing, I created this little variable just to make it convenient. And I'm going to plug that right here. So B has a value of 21, which I know is the length of my bone. Okay, so now this gamma angle is the angle that we have here. So we just need to take this transform and add this rotation to it. The way I like to do it is I like to use the mech absolute node, because personally I can never remember the order of operation when I do matrix multiplication. So I find this node very convenient because it's telling me this is the parent and the local is the offset I want to add to the parent. So I know I just need to plug my extra rotation over here. I can't use quaternions directly, so I'm just going to have a Euler node. And in this case, I know I want to rotate on the z-axis, so I'm going to plug it right there. But be careful first. You can see here that this node returns the angle in radians when the Euler node takes the angle in degrees. So we need to convert this into degrees. And I can plug that here. And let's now draw this transform instead of the previous one. And you can see that it has rotated a little bit. But it looks like it rotated in the wrong direction. So all we have to do is to add a negate over there. And now these transforms match perfectly the first joint position. So if I move that, notice how this starts rotating because this angle becomes bigger as this distance gets shorter. And you can already see that it's the behavior of an IK. So now all we need to do is to create the second and third transform, and we should have our IK solver. So the second transform, if we think about it as a child of this first transform, really all it is the length of that first bone to the length of the first bone on the x-axis. So I'm going to grab this transform that I just created, and I'm going to transform the location. Transform location, there you go. And I said that on the x position, I want to have the length of my first bone. So I'm gonna grab get length of A. I'm gonna plug that here. So that should give me the position that I'm looking for. Uh, so we could draw that position already and see if it's where we expect it to be. And it is, but it's not pointing yet to the IK. So in order to do that, well, we could just do another aim, and that's exactly what we're going to do, aim math. So now we know that our input transform is this position. The up vector and the IK are still what I want to use for my targets. So primary is going to be my IK, and secondary is going to be my up vector, just like that. And remember to change the axis on the up vector. And let's now plug this. And there you go. Already looks very much like an IK. And I can roll it, and everything follows properly. So now, let's make it a little bit more interesting. First of all, we need to do the third transform. And I like to do it, again, kind of the same way, where I'm going to grab this transform and offset on the x-axis, but this time using the length b. There you go. So that's going to be my initial position. And so again, if I just draw this position, it should match my my IK position. Well, it's not matching my IK position all the time. It's only matching it when I'm not overextending, because I locked it to be only on the x-axis, just the distance of the second bone. But that's exactly what I was looking for. But for its orientation, I just really want to use the IK orientation. So I'm going to grab my IK control, and I'm going to grab its rotation. And if I plug that here now, oops, it's rotating with the IK, which is exactly what I want, but it keeps its length. So we just created an IK with no stretch. Yeah. So maybe we do want to add the stretch, or maybe the first thing I could do as well is connect the joints to those transforms. So let me just grab them quickly. The upper arm set bone. I'm going to plug that here and plug that transform over there. And the lower arm set bone. I'm going to grab this transform here and add it there. And the last joint, set bone. And for this one, what I'm going to do, because I've plugged directly inside the rotation and translation, I'm going to use a reroute. This way I can plug my my results into my drawing and my actual bone rotation. Okay, let's just double check. Yeah, we got an IK here. So now, if we wanted it to be able to stretch, what do we need to do? Well, we want it to stretch, so we want it to scale when the distance between the root and the IK is longer than the sum of those two distance. So I'm going to grab the lengths A and B, and I'm going to add them together. Not this add, this one. And I have the distance between the IK and the FK. And so what I want to do is I want to do the ratio between both of them. So I'm going to divide this guy by the sum of those two lengths. So it means that this is going to be 1 when it's stretched. It's going to be bigger than 1 when it's overstretched. And it's going to be less than 1 when it's supposed to bend. So what I'm going to do is I'm going to force it to be always at least 1. And I'm going to plug that into the scale of this transform. So here I can just scale the x-axis, and over there I'm going to need to scale, let me think for a minute, I'm going to need to scale here. So I'm just going to do the same again, where I'm going to do a reroute, because now I need to decompose my result. So I'm going to put that here. I'm going to put that there. Oh, my reroute collapsed. Okay, so let me do that first. So I'm going to grab the rotation here and the translation, because that's not going to change. And then I'm going to take the output, plug that here, here, and there, just like we had. And on the scale X, I'm going to add the ratio that I had before, that I just calculated. And see, now it behaves just like if I was stretching the IK, but only when it's going over 1. So this here is what preventing it to compress when it's under 1. Yeah, and that's it. That's the whole setup that we were looking at the beginning. Now, why would you do that when you already have the basic IK node? Well, I mean, this is totally fine, and you should use this node whenever you can because it makes your life much easier. There's no doubt about it. What I wanted to show here is just, for one, how easy it is to do this kind of math with control rig, which I find super useful. I think it's important to know the math behind your rig because if you have a good understanding, you will be able to do a lot of crazy stuff that maybe a basic IK node can't do. You will be able to do more than just that. And that's kind of what I did on the BungeeMan, where I created my own IK solver because I added some feature that the basic IK doesn't have, such as, for example, I have softness, which allows me to have this kind of anti-pop on the IK solver, where I get a much softer transition between the stretched and the bended position of my IK. I added the reverse, which is kind of a funny way to reverse the chain, and now it's bending backward. If you set it to 1, if you set it to 0.5, you get this chain that never bends, which again, I mean, it's just some flexibility that I have. I have a maximum stretch limit, I have a slide, and I could do other stuff, but it's kind of the point is now that I have access to the math behind it, whatever I come up with, whatever idea I come up with, I can directly modify my graph to accommodate those needs. That's it. I hope you liked it, and I'll see you next time.